All right, Daniel's on his second talk of the day. He filled in for someone earlier. So Daniel is a scientist at NIWA. I think they've just merged into Earth Sciences, but I'll let him tell you about that. He's going to talk about field testing of an automated detection system for submerged weeds. Cheers, Dan.
Thanks for that. Kia ora koutou katoa. I won't talk too much about the merger, but yeah, we're now Earth Sciences, effectively with a NIWA stream and a GNS stream until it all comes together, which will take a little bit of time. But today I'm going to talk about field testing an automated detection system for submerged weeds that we've developed over the last couple of years. Some of you might have seen this previously, but we've done some recent field trials, so I thought opportunity to give an update of where the system's currently at. Okay, so a bit of background, particularly regarding aquatic weed management. Effective management requires surveillance strategies that are operationally efficient, management strategies that can be implemented on a national scale by multiple agencies. And as we've heard from our keynote talks this morning, early detection is critical so that those eradication strategies can be implemented in the early stage of invasion. That's the most cost-effective phase of conducting management. So that's where we're focusing this particular bit of technology. This is what I'm talking about. This is Lagrosiphon major at Lake Whakatipu in Queenstown. On the left-hand side there, you have an individual plant of the South African waterweed, Lagrosiphon major. And then on the right there, you've got a late stage of invasion at Lake Dunstan. And that's what we're trying to prevent. If we can pick it up early, in this early stage of invasion, we can remove that by hand and prevent this situation from occurring across the country. And, there's a lot to protect. There's very diverse, low-growing, very unique native aquatic plant species that we've got present here. And as you can see on the right there, once you get those invasions, they're monocultures, surface reaching, that are causing a whole range of impacts, whether that's, access to water bodies, social values, economic values, cultural values, and of course, environmental values by displacing our native species. Current surveillance methods are heavily reliant on divers to detect these incursions. So this is a map provided by Boffa-Miskell at the bottom here. And you can see the divers are being, those blue lines there are where the divers are being towed through a certain area. And in high-risk sites like that, that can occur three times per year. And this is only on one part of one lake. So, you expand that out, the resources that are required to conduct that is extensive. And this is what we're trying to detect and what the divers are removing. So it's these individual plants in amongst those lower growing plant communities. What the team at NIWA Earth Sciences has done is develop this prototype detection module, and it's pallic encased with a computer inside it that's been trained what to look for, with submersible cameras attached to it. And when it's deployed in the aquatic environment, it'll detect the target that it's been trained to detect and then drop a waypoint on top of that target, and then we can provide that to management agencies to conduct management at those specific sites. So overall, this is what we're trying to do. So detect targets on the left there in an early stage of invasion using the detector module deployed on crewed or fully autonomous vessels, sending our divers back to those specific points instead of conducting whole of lake surveillance to prevent these situations from occurring. I thought it's good to go back and see the development and the science phases in this project. So this was some work that we did initially. We wanted to see, can we develop an algorithm that can detect the target and drop waypoints in real time as we're travelling down the flume facility. And this is at our flume facility in Kirikiriroa, Hamilton. And you can see as we're travelling down, it's detecting there's a few false positives in there, but it gave us the confidence that yes, we can detect the targets, drop those waypoints, and then develop those algorithms further from that initial work. We then had an opportunity to test the system out. There was an early incursion in the Frankton arm at the Frankton Marina. So we deployed the system in that situation there. So here you can see this is all real time. So it's dropping its waypoint. The numbers that are associated with that is the confidence interval of the algorithm. So if you're getting a 0.9, it's 90% confident that that's what the target was detecting. Following that initial field work, we went back and we did some benchmarking. So we had a whole bunch of imagery that was collected by divers. What we did is we selected a whole bunch of imagery. We had experts go over the imagery and locate the lagrosiphon apical growing tips that are growing in amongst the other vegetation types. And you can see it's quite difficult. So on the left there, I've just circled what we would have done, gone through and identified those particular targets, and then across the same imagery, run the algorithm at different confidence intervals. So you can see in the center there, at a 50% confidence interval, we've got, it's picking up the lagrosiphon that's present in that image, but also down the bottom here, we've got a false positive detection because we set the algorithm at 50%. So it's picking up more targets. When I refer to false positives, I'm referring to it's picking up something that it wasn't meant to. Okay, and then if you run it at 80% confidence interval, it's picking up the targets, but it's also missing a target here, but it's dropped out the false positive detection down the bottom there. So there's this balance between, we want to be, high confidence of detecting, greater than 95% hopefully by the end of this, but also reducing the number of false positives we've got, because if we've got too many false positives, it's going to make it really difficult. We can, each time that it detects a target, we can drop a individual, like an image that's associated with that target. So there can be some ground truthing associated with that to sort of limit the impacts of those false positive detections. So what did we find from that benchmarking? So at the 80% confidence threshold, we were getting quite high levels of detection, 85 to 90%. But what we saw as we added more instances of lagrosiphon to the algorithm, we had an increase in our false positive rate. So the more diverse that we made those algorithms, the more false positives that we were getting. So we have to be very aware of that when we're continuing to develop these systems. Okay, so in regards to the work that we've done more recently, so we took the algorithm, we had two algorithms that we wanted to test out, but we took those to the field. So we wanted to run this stuff, not just in the bench testing, we want to see how well this system's doing, in the real world. So here we have the field trials that we conducted. We selected 6 sites, 3 in the Caldo River. All the imagery that we've used to develop the algorithms have come from the Caldo River and Lake Whakatipu. And then we also had 3 sites at Lake Wanaka. And that was to see how well the algorithm would do in a situation that it had never seen before. So how generalized is that model? At each site, we tested 2 algorithms. We tested different boat speeds. So how does the system cope at operating at 1 to 3 knots? The camera distance to the target, plant conditions. So if the plants are dirty or if they're clean, does that affect the rates of detection? As well as we repeated each of those transects multiple times. So we had, so if you can see there in the image, we set up a transect line between the buoys there. In the center, there would be an isolated infestation of lagrosiphon, and then we just ran across it 32 times to account for each of those variables at each of those sites. So quite a decent data set. And so this is an example of what we did. So traveling up over the top of with the cameras deployed over the top of that lagrosiphon bed there, and then the algorithms detecting the targets in real time. In regards to the dirty and clean plants, this is what I'm talking about. So On the left there, you have dirty plants covered in sediments, glacial flour, algae, and would run the algorithm over the top of that and then clean those plants off and then run it again and see if that's affecting the ability of the detector. Also collected a range of other information associated with each run. So the depth to the bottom, camera depth, plant heights, number of apical tips that we're running over on each transect, water clarity, ambient light levels, because if it's dark, does that affect the detector? And then we set the confidence threshold at 80%. So what did we find? So in this image here, in this chart, we were getting, at some sites, we were getting quite high levels of detection. In regards to the two different models, Model A was an older model than Model B, so we developed it further. Interestingly, Model A had more instances of lagrosiphon trained in that model, and Model B, it was nearly half the number of training instances of lagrosiphon used in that model. But what you can see there, so on the left you've got the detection rate, on the x-axis you've got the camera distance away from the targets and at each site. And so what we're seeing there is that one limitation that we've currently got, a major limitation that we've currently got, is the distance of the camera that it needs to be towards to the target. So we were looking at, we needed to be within 0.4 meters of our target. And there are ways to improve this over time, but this was our first go at really evaluating where we're currently at. And the imagery that's been used in the training has all been collected by divers, so you're generally up quite close to that, so that's probably biased the way that the current detector's been developed. Okay, so in regards to our false positive rate, so Model A, the initial model, we had really high levels of false positives. So so on the right here, the top image, it's picked up that as lagrosiphon. That's not actually lagrosiphon, that's our native milfoil species. And Model A produced a significantly higher numbers of false positive detections than Model B over the sites that we assessed. This is just some underwater image to put it in more realistic. So this is what the camera's seeing and detecting the target. So there was a bed of lagrosiphon at the start of the transect. You might get sick watching this, but we'll see how we go. There's and then you've got your very low growing turf communities, and then another bed of lagrosiphon. It's picked up. It's not picking up every apical tip, but in general, if we're picking up that patch, we don't need to detect everything. But when it's at really low abundance, you want to make sure that you're picking up every individual tip. More complex environment in the Kawerau River. So here you have in amongst our native Potamogeton and again milfoil, and you can see it's picking up that lagrosiphon in amongst. So this is all Model B, where we've got minimal false positives. There was one there. But you can see it's quite complex, quite difficult to see, and in this particular instance, it's picked up a very small plant of lagrosiphon in amongst that quite high cover submerged vegetation. Last one, and here we have sort of a moderate density of lagrosiphon. As we're travelling on, in this particular instance, we had a variable camera system, so we're able to lower the camera system down. By this time, we'd sort of realised that there was a limitation of the current system. So we were. This is just an example of what how we see it progressing, but also improving those algorithms. So, in summary, camera distance to target. Both models detected more lagrosiphon when the target plant was close to the camera. It is the major current limitation. False positive detections. Model A produced significantly more false positives than Model B, so we'll be developing Model B further. Increasing image resolution when we're developing the algorithms, as well as increasing the number of layers that we use for feature extractions in the model. There was minimal difference in detection rate between the clean versus dirty plant, so that was really good. The boat speeds 1 to 3 knots was still working at the higher boat speeds, and then there was, between the Caldo River and Lake Wanaka as well, it still worked in Lake Wanaka where we hadn't input any training data into it, so it's showing promise there. It's a compact module that can be deployed on autonomous uncrewed surface vessels like the one on the left, or remotely operated submersible vehicles. Our marine biosecurity team has been developing the system for Clerpa and a couple of other species as well. And then into the future, looking for the use of fully autonomous underwater vehicles as well, and integrating that. So for us, the next steps is to develop robust detection algorithms for lagrosiphon and hornwort. And we're working with DOC on the hornwort detection algorithm, increasing that distance to target detection. And we're working with the instrument systems team and our AI deep learning team, who are leading the software and hardware developments, and then carrying out those desktop evaluations prior to going to the field. But those field trials in the real world environment is really important, and ultimately that's where we need to be. So we need to be testing it out as we go in those systems as well. So yeah, thank you very much. Just thank the NIWA Freshwater Biosecurity team, the Instrument Systems team, and the Marine Biosecurity and Fisheries teams, and our international collaborators, as well as recognising Department of Conservation for contributing to certain aspects of this project. So yeah, thank you.